Yeah, so I'm the director of the National Center for Supercomputing Applications. The EXCEED is one of the projects of NSF that is homed at the National Center for Supercomputing Applications. So I wanted to first set the stage. I'm really interested in participating in this workshop to learn from you. I'm not an economist, so I'm going to cast what I talk about from what I know, and then I hope to learn from the rest of you. I do have a lot of experience in developing algorithms, tools, and applications, and that's, again, one of the reasons I want to hear what it is your community needs, what would help accelerate you as much as possible. I have been doing this for a long time, longer than some of you have been around. That picture is from the 1985 Intel annual report. It's me and a graduate student awkwardly leaning over a 128 processor parallel computer. So this has been going on for a long time. I think most importantly, currently I'm running this center whose mission is to essentially bring advanced computing to all areas of scholarship. And I'm particularly excited about the opportunities to bring advanced computing, and I'm saying advanced computing instead of high performance computing because I think what's really most important is taking advantage of the digital revolution to advance scholarship. In some cases, this means high-performance computing. In other cases, it means bringing to bear the tools that we have to unusual problems. And just as an example of that, we recently helped create a new primary source in medieval studies. Turns out that pilgrims would scratch graffiti on stone columns in churches and cathedrals. And this was known, but that data was acquired in a fairly ad hoc fashion. People would sort of sketch what they saw. Of course, you could do laser imaging, image enhancement, and so forth, and get very precise, no observational bias kind of details from that sort of information. It's not really high-performance computing, but it is the use of advanced computing tools. And so as we think about what we're doing here, please don't put your mind in the straitjacket of, oh, what I do is not high-performance computing. Think of it as the use of computing to solve your problems. I am going to assume, particularly having looked over some of the talks, that there's a wide range of HPC experience here, so that's why I'm going to be talking about the trends. If you have specific questions about tools or how one would go from where you are to greater scale or greater use of HPC, I'm going to be here all day. Please take advantage of that. And then finally, there's a lot of support for making use of HPC resources. Last year, you had some really great talks. I went through and looked at them from some of the staff at EXCEED about the resources that are provided by the National Science Foundation for the use of these systems. I really recommend that you take advantage of those and look at those. So what do I mean by high-performance computing? So everybody has a different definition. People, of course, tend to focus on the definitions of the kind of computing that they use. The definition that I'm most comfortable with is that it's computing where performance is important. And it could be important because you have to get an answer in the next 30 milliseconds. It could be important because there's no way you'll be able to get the answer in less than 10 years unless you pay attention to performance. You've got a whole spectrum like that. And there are many different cuts in terms of the way we look at this. One common one is to talk about capability and capacity machines. So capability systems are massively usually massively parallel computers that bring a lot of computing power to bear essentially on a single problem, single application that's running, so that they have the capability to run those problems. Capacity machines provide a lot of aggregate capability, but it tends to be used across a greater swath of concurrently executing applications. And so that swath of currently executing applications might, for example, be part of the same study, but it might be doing uncertainty quantification or statistics on the solutions and so forth. Another way to look at HPC is by use. So sometimes we talk about tightly coupled machines. These are machines that are organized in a way that they can communicate frequently and with great efficiency so that they can remain connected and coordinated as they're working on the same problem. And I'll give a few examples of those a little later. Another mode is often called high throughput. This again is an approach where you may have lots of separate or nearly separate tasks that have to be computed. You might have millions of those or billions of them, and you need to run each of those, but each of those individual tasks doesn't have to interact at all or very much with the others. And so the real challenge there is I've got a huge lump of work to do. I have to get that through the whole system. And of course, everybody's talking about big data and machine learning these days. In some sense, those are subsets of these, but in other senses, it is different. In particular, talking about the availability of different kinds of data. One of the things that has transformed big data is this sort of availability of larger sets of data, the ability to move more of the data around, plus the combination of enough computing to be able to implement algorithms that have been around for a while but had been computationally out of reach. And it's maybe one of the other things that's been very exciting about HPC is the great growth in performance, so that ideas that were really interesting but infeasible over a decade or so can become quite practical. And then another way of sometimes looking at these systems is sort of by configuration. Are all the computing elements the same? Are they a mixture? Does that mixture contain things that are often called accelerators, which are processors that are optimized for certain kinds of operations? And of course, there's the cloud. And I'll say a little bit more about the cloud towards the end. Maybe one of the most important things here is that there's no single metric for high. So how we define high depends on what you're looking at. I took this diagram out of the National Academy's report that I co-chaired on the future of cyber infrastructure for NSF through next year. Since I drew it, I figured I could take it. And it's a very approximate figure, but it's intended to point out that in addition to the compute axis, so the number of, say, floating point operations or integer operations that you need to perform for some sort of application, there's also there's an axis for the I/O and file performance, so the ability to move data in and out of the system. And then there's another axis for essentially how tightly coupled it is. How efficiently can you bring all of the processors to bear in a big system on a single problem? So there are a lot of examples of the use of HPC. This is, even what's here is a tiny subset. My own research area has focused on the solution of partial differential equations. One thing to note is what might not be a terribly dense mesh, say 10,000 by 10,000 by 10,000 grid, is already a terabyte with 1 byte per grid point. So you need 10 terabytes effectively just to hold a single field value. And that's not a terribly refined mesh. Now, of course, there are lots of techniques. One can use higher order methods, one can use mesh refinement and so forth. But many simulations are struggling with just the spatial resolution that they need. There are applications today that require over a petabyte to represent the data on which they're working. Right? And so HPC makes those systems available. So it's not that there are problems that require a petabyte and they're out of luck. There are problems that require a petabyte and they're running. So that's one of the things that this revolution in high-performance computing has given us. In-body simulations range from molecular dynamics for biomolecules. One example that we did on our big supercomputer in an early test phase was we ran what's called the HIV capsid. So it's the shell that the HIV virus uses to protect itself. The research goal there is to understand the geometry of that, because the way a lot of drugs work is a combination of the geometry. In fact, often a large part is the geometry and then some of the chemistry. And so if you understand the structure, you can start thinking about how you might attack it. a lot of stuff is used for the analysis of large data sets. And so this example is the reference elevation model of Antarctica. This was done by Paul Morin and his colleagues at the University of Minnesota using our Blue Water supercomputer. The accuracy of this map is 1 to 8 meters. That's better than the maps that we have of the Western United States. Done at lower cost because it's all based on taking satellite data and essentially doing stereo imaging, and by looking at the differences, figuring out what the elevation is. So not only is it cheaper, but you can do it as often as you can afford the computing. And so you can add a time axis to the maps that we get. Other areas of science are doing this too. We're a big part of something called the Large Synoptic Survey Telescope Project, which is a primarily NSF funded project with the Department of Energy primarily responsible for the camera, which is, by the way, the highest resolution camera ever made. That will do the same sort of thing for astronomy. It will image all of the southern sky that it can see every 3 days, looking for changes. And this is something that astronomers haven't really been able to do in the past because it takes so long to gather the data, so long to analyze it, so long to look for it. In fact, our requirement as part of that project is to detect a change and send out alerts within a minute of the image being taken at the telescope, which is in Chile. And so high-performance computing has really made it possible to transform the way we do a lot of this science. But HPC is also used, as I mentioned, for large collections of separate computations. So if you're trying to do something like uncertainty quantification, understand the variations in what you're simulating, you may need to run many models, hundreds, thousands, millions, depending on the science. Each of those may not be very big, but in aggregate, they require a lot of computing power. As I view it, HPC applies to that as well. I put this slide up somewhat to scare you and somewhat not to. Because one of the messages, part of the reason I wanted to talk about trends is, as we'll see, there's been really about 3 decades of stability in the computer architectures. And that stability is coming to an end. So that's both scary, but it's also an opportunity. And it's an opportunity, of course, it's an opportunity for people like me, a computer scientist, to find other ways to use that. But it's also unleashed a lot of innovation, which provides opportunities to the scientists. So just to go over these very quickly, just so you can understand what are the sort of salient features of these. On the far left, this is a machine called the Sunway Taihu Lite. It's one of the that's the processor in one of the fastest machines on the planet. It's a very heterogeneous thing, so it has 2 kinds of processors. One is intended to work effectively on large arrays of data. Another processor is intended to work on everything else, which is hoped to be a small part of the computation. It doesn't have the kind of support for working with memory that most of the systems that you're familiar with have. Without getting into the details, most of the systems that are used today put a lot of energy and effort, cost, and impact on the performance to shield the programmer from certain details. It's an interesting question for a bunch of economists, whether that's the right decision to make. In the case of this system from China, for a number of reasons, particularly schedule, they couldn't do that. So the processor is simpler. It was very fast. It took much less time to produce and deploy than is typical for processors done in the US. This next machine is actually an abstract machine. Was put together by the Department of Energy to start thinking about what the next generation of big machines would look like. And again, the feature here, details are less important. The feature here is that it's made up of different kinds of processors. And we'll see why people have been driven to that. I did want to mention a very different approach. There's often statements made that it's very difficult to design processors. It takes 7 to 10 years to deliver one and whatnot. So this is the Adaptiva Epiphany 5. It's a 1,000 processor, very high power efficiency. Did not take that long. There's an earlier version of this with, I think, 32 cores, which you can buy on Amazon and was funded with a Kickstarter. So how did they do that? That processor has nothing except just what it needs to do the set of problems that it's interested in. And so focusing again on having the processing elements do just what is necessary and moving away from fully general purpose systems that try to shield the programmer from a lot of the details is one of the trends we see, and it's going to be driven by, in many cases, the economics. Again, both the cost in terms of schedule and dollar cost for putting them together. This last one, this is a diagram of the node from one of the 2 recently delivered machines for the Department of Energy, currently ranked. This diagram is from the machine ranked number 2 on a list that I'll talk a little bit more about. It uses a Power 9 processor from IBM plus 4 NVIDIA graphical processing units. One of the reasons I think that's interesting is we have a small system, just 16 nodes, intended for deep learning research, and it is essentially the same diagram. Ours also has one other little wrinkle for experimentation. The point here is that HPC is not really that different. The pieces that go into HPC are in many cases similar to the pieces that go into your laptop. So it was nice having the Power 9 is actually a wonderful processor, a little more expensive, but you get some things for that. But a lot of the needs in HPC is getting performance out of the same kinds of environments that are running on your laptop. Okay, and then as we look, for example, at what might emerge from China, what is emerging from Japan is their next generation of extreme scale systems. They're all heterogeneous for some definition of that. So they all are a mix of kinds of processing elements that have been designed to optimize for different operations. So I want to say a little bit about some of the trends. So one of the things that's been maybe most remarkable about computing over the last 30 or 40 years has that computing power, by one measure, has been growing exponentially. And I mean exponentially mathematically. So we sometimes see in the popular press exponentially meaning fast. But I speak as a mathematician. And there's a consequence of that, is that in many cases, if your application didn't run fast enough, the best solution was to wait, because exponentials are wonderful. And this is sometimes described as a consequence of Moore's Law. Has everybody heard of Moore's Law? Okay, so now I want to make sure that you actually heard of Moore's Law, because it tends to be ascribed to performance doubles. For example, one definition that people will say, oh, Moore's Law means the computing power doubles every 18 to 24 months. Okay? Wrong. That was never Moore's Law. Moore's Law was only about the essentially the feature size, the density of components on a chip, more or less at fixed cost, and that the feature length would decrease exponentially for, he thought, maybe 10 years or so. What's much more important is it turns out as you make features smaller, it means that you can make them operate faster. You just sort of think that if you've got a switch, you've got to move it, or you have to move the electrons across it, or if you have a physical switch, you have to move the switch. You make the switch smaller, you can move it faster. So there's a thing called Dennard scaling, and the coupling of Moore's Law, which was making the features smaller, And Dennard scaling, which said that you could make things then faster, did lead to a lot of performance. But we'll see that that advantage has ended. Of course, the reality is much more complex. We tend to focus on the floating point and integer operations. They're easy to measure. As a numerical analyst, we always make our students do computational complexity estimates in terms of the number of floating point operations. The aside is that's doing our students a tremendous disservice because it turns out that for most of the numerical applications, what controls the performance, which actually is much more relevant in terms of understanding the performance of the algorithms, is the complexity of the data motion. And so, and it's not always the same. And in fact, one of the key benchmarks has a very big difference between those two, and it's led to some misleading conclusions. Okay, maybe so things like memory access, I'll say a little more about that, and access to data is often more important. So maybe the important thing to note is that Moore's law, it's not a law, but it has become an imperative. So it has helped drive the industry to find engineering solutions to hard problems in order to stay on this law. We'll see in a moment whether they've done that. Another interesting way to look at computing in the sciences, this is a thing called the Branson Pyramid. This was from an early report, originally in 1993. This picture is from an update that was added. I think the original figure came from 2006, and it was in a report to, I think, to NSF in 2011. And so the original one had like a 1 teraflop system on the top. That was a leadership class machine. So leadership class machine being the fastest machine that you could possibly have. Down to center scale, campus scale, and sort of desktop scales. And between the original and the update, that went from 1 teraflop to hundreds of teraflops, 10 teraflops, 1 teraflop, and tens of gigaflops. If you update that today, it's hundreds of petaflops for leadership class, tens for center machines, ones for 1 petaflop or so for campus level systems. You can get desktop machines now that are about 10 teraflops, and those tens of gigaflops, that's what your laptop can do. Okay. So, and what I've left off of this are these commercial data centers. It's very hard to find out exactly what their capabilities are. They tend not to talk about them, but you can look at things like the number of servers they claim to have or the amount of power that they consume. So today's leadership class machines consume somewhere between 10 and 20 megawatts. Google, I think Google's talking about overall its data centers consuming about 1 gigawatt. Okay. So I've been talking a little bit about high. How do we, what is high? How do we measure performance? So in high performance computing, the best known is something called the high performance Linpack, or HPL. There's a website, top500.org. Been doing this list for 26 years. This benchmark solves a system of dense linear equations, dense one where essentially all of the matrix elements are non-zero. When it started 26 years ago, that was representative of a lot of scientific computing. Almost nobody does this kind of computing across an entire machine anymore. Yet we still run this benchmark. There are some other benchmarks. There are also maybe much more relevant benchmarks that are drawn from application sets. But one of the things that's really interesting about this HPL benchmark is that it has been collected for 26 years, and there's a lot of data. And so I pulled these two, they're basically the same chart off of the website, showing so that the green line is the sum of the performance of all 500 machines on the list. The jagged thing in the middle is the performance of the machine at the top of the list, and the smoother line at the bottom is the performance of the machine on the bottom of the list, the number 500 machine. And then over here, they did a curve fit and drew lines through it. So this would probably be a great example for your class of how not to do curve fitting. Because we can look at it like this. So let's focus first on the right. So this is just the bottom of that list. So the blue curve that you can barely see there is the same as the blue curve here. That's the performance of the machines on the bottom of the list. And what you see is that before 2009, it was essentially a straight line. And after 2009, it was essentially a straight line, but with a different slope. What happened there was the end of Dennard scaling. This is when processors stopped getting faster. You may remember 2006, 2007, processors were 2.5 to 3 gigahertz. What are processors today? They're 2.5 to 3 gigahertz, maybe 3.5. Right? The deployed machines, there's a little bit of a lag there. A nice thing is I look at this data every 6 months when it comes out, and so I just add more data. I haven't redone the fit in years. Let's see. There's the most recent data. And so again, the slope is a good fit to the red line since 2009. The other one I want to point out, because there's a lot of people, Moore's law is, everybody says Moore's law is either dead or it's doing fine. I found this wonderful graph in an article in Scientific American in 2004, and this was essentially right before Dennard scaling started to hit. And although it's hard because of the colors here, the projected clock speed for like 2019 is about 70 gigahertz, not 3. There's similar things for the gate length. So what has happened is Moore's law really has ended if you think of it in that very rigid description. What has happened is that Moore's law has been permuted into a statement that we will continue to make progress, which is why Moore's law will never end, because we will continue to make progress. I did want to say a little bit about then. These are some examples of machines on the top of the list. I'm going to go through these quickly just so you can see some of the progress. So on the left is the high-performance Linpack, which is the dense matrix, no longer representative of much of real science. On the right is high-performance conjugate gradient. This is a sparse matrix problem. This is a much more recent benchmark, so there isn't as much history. And however, it is much closer to what a lot of science applications, particularly ones that use simulations from PDEs, use. And an interesting thing is to match up the the machines on the left with the machines on the right. And one of the things you can see is that while machines that are powerful supercomputers are powerful supercomputers, doing well on the high-performance Linpack does not necessarily mean doing well on the conjugate gradient application. And one other thing to note is that the top machine on this list didn't even make the part of the list that I've showed you for the high-performance Linpack. More recent systems given us something like this, where currently, yes, these two top machines are the same as the two top machines, but then again we see that the performance on the Linpack benchmark, the top 500 benchmark, is not as indicative of the performance that applications are likely to see. There are some other, oh yeah, and I should say that in the system, these leadership class machines, sort of the most powerful machines, are really the top 4. There's a significant break, like a factor of 3, to get to the next machine. Again, there's a number of examples of different benchmarks. There's one called the Graph 500, which looks at, there's a breadth first search and a single source shortest path algorithms that have been run on a variety of systems. It's not as exhaustive, so it's hard to draw up the same sort of statistics. But again, what's good on this is not the same as what's good on the high-performance Linpack. Another thing to note, you can look at the top 500 data, and they've got ways to look at a number of the parameters over time. And one thing that's interesting is this one. This is the use of accelerators, so the use of specialized processors targeted to a sort of subset of the application. The left is based on how many systems. The right is based on the total performance of the systems. The most important thing to note here is that while it is true that a lot of these systems are still sort of the same sort of processor that you have in your laptop, except design, what's called server version of the processor, there's continued growth in the use of these more specialized processors. And the other thing I should say, so this phone as a computer is in fact in every way more powerful by all of the numbers, however I want to measure it. It's a better computer than the supercomputer that was on one of those earlier versions of the top 500 list and was a supercomputer at one of the nation's weapons labs. So just this phone 30 years ago would have been more powerful than the most powerful machine on the planet. And so that's, and part of why that is, the processor in here is very heterogeneous. There are lots of specialized pieces of this to handle different parts of different problems. It's one of the reasons that it works so well. So one of the messages here, what are the messages? One, you have to be careful with benchmarks. So you should be if you're looking at performance, you need to be looking at what makes sense for you. Another is that as we're going forward, it's going to be increasingly important to think about how algorithms and applications map onto the sorts of processors. So looking at this, we see a growth in the use of these specialized processors, often for GPUs. The Chinese systems are based on digital signal processors, which is similar to but different than a GPU. The GPUs grew out of the gaming market. It turns out anybody who knows about computer graphics knows that a core operation there is a matrix multiply with a 4x4 matrix. And then doing a zillion of those. Digital signal processing doesn't have the same building block, but it has a lot of the same elements. And one of the other things is HPC systems are really not that different. So I want to encourage you, don't be scared of them. A lot of the features of the systems are similar to what you have on your laptop. We do focus, I think, too much on the floating point operations, I/O and memory. I can give a whole talk on how one can look at thinking about the memory that you move in these numerical algorithms to see that that provides a much more accurate representation of performance. In fact, in 1999, we won there's a prize in high-performance computing called the Gordon Bell Prize for reaching very high performance on some application, and we won a prize there for a computational fluid dynamics application that had an unstructured mesh. The key thing there is that people didn't think you could make that run fast. What we did was we showed that it was running as fast as it could, because if you just thought about, I have to move data from where it is to where I can compute on it, do my operations, and put the result back, and you looked at how fast the memory system was and how fast the operations were, it turned out we weren't getting 5% of performance, we were getting 95% of performance. Now, we were only getting 5% of the floating point performance, but we were getting essentially the full performance of the system. And that, again, is one of the things that's important is we look at high-performance computing as focusing on performance. One has to look at the right kind of performance. There is a lot of software, both applications, libraries, and tools that have been optimized for this. So there are a lot of people in computational science working with, for example, PDEs that make use of software libraries that manage distributing the data across the systems, doing the communication, doing the linear and nonlinear system solves, and so they can focus on the science. So it's important to also look for existing tools that can help you build up the applications that you need. So this Dennard scaling ended more than a decade ago, and so as a consequence, what we see is that the individual processors haven't gotten much faster. We've been able to continue to claim more and more performance. Where does that performance come from? It has come from parallelism. That is harder. It means the algorithms have to have enough concurrency. Codes have got to be written to take advantage of that. Moore's law really is ending, despite what certain large companies want to tell their marketing people. But because it's been redefined as progress, it will never really end. It will just continue to slow down. Again, as has been mentioned, the ability to aggregate and share and work with data is at least as important. So again, I sort of encourage you not to think HPC is that floating point stuff. Right? HPC is that performance stuff. And the specialization is driving computer architecture. So the good news about that is we're finally getting innovation. As a computer scientist, it was always pretty depressing over the years. In fact, I knew people who would have a group of coffee mugs for failed computer companies. You know, what people would say, oh, I can make a faster computer, and I will do something really clever. And by the time they had delivered it, the exponential had overtaken them. Well, with the end of Dennard scaling, that stopped. One of the reasons that GPUs have become so important is that they were a different solution. They were an innovation, an early innovation in that space. They have simpler processors, but more of them. Often they run at a lower speed than the general purpose processors, which gives you certain other benefits. Your phone completely depends on specialization. And so going forward, this has become more and more important. Okay. So first question I usually ask people who say, I want to use HPC is, really? I sort of hope so. But in many cases, it's really not that. It may not be necessary. So one of the most important things to do here is to really understand what your need is. So if you were an experimentalist in another field, you would go through a fair amount of work to design your experiment. One of the problems with computing is it's too easy to write code and run it. And particularly if somebody else is paying for the computer time, why not? Right? That has developed a number of bad habits across the community. So no one has been immune about this. It's important to be thinking about how fast should this code run? How fast could it be running? And more, that's going to be important as you start looking for resources on which to run your computations. And one of the important things in looking at this is just looking at the computations, looking at the floating point that you're doing, or maybe at the integer operations you're doing, is often not a very good predictor of overall performance. You have to look at some other things. You have to look at, again, at how memory is moved in and out of the system. You may have to look at the data access. If you suddenly running on a system where you're charged for data access, you really need to be looking at that. And you need to look at the available concurrency. So some algorithms just don't allow you to take advantage of the parallelism, and so having a 100-core chip on which you can use one core, but you'll probably still get charged for 100, isn't necessarily going to help. I do want to say there are people who work very hard at producing very, very accurate models of performance. What I'm arguing here is that what you really need is decision support. So you only need an approximate model, and it needs to only be good enough to answer the question of, can I afford to run this, or can I convince somebody that it's running well enough to be worth putting it on their system? Some of those models are getting a little more complicated. I did want to, for people who are doing MPI programming and distributed parallel programming, there's a very simple model that has been effective for at least 30 years. In this paper, we show that because of the architecture of modern computer nodes, one needs one more term to recapture the accuracy in the model. So for the advanced distributed computing parallelism users, I suggest you have a look at that. It's also argued that it's more important to use the right algorithm than to have the fast machine. There's this interesting chart. This originally appeared in a Dewey book on the science case for extreme scale, the scales report, which contrasts the performance increase, calling it Moore's law, but mostly due to Dennard scaling, from an early machine up to what was then the present day, with the algorithms for solving a dense linear or sparse linear system arising from a 3D PDE, starting with banded Gaussian elimination, so just use the part of the matrix that's non-zero, all the way up to something called full multigrid. And what you saw when you did this was essentially an exponential increase in both. That you were basically, you could either take an ancient machine with a modern algorithm or a modern machine with the ancient algorithm to get the same performance. So a lot of people like to look at this. I do like to point out the asterisk. By the time we get to full multigrid, we're doing O of 1 work per data value returned. There isn't a lot of room to carry that further. And so there is a need to use in more modern machines as the algorithms get to be this good. Another thing, another trade-off, and I want to say up front, there's not necessarily a right answer in here. Another trade-off is between performance and productivity. So this was a study published at SIGMOD in 2014, looking at some graph frameworks, and they had one that they called native, which was that they wrote the problem using low-level stuff, and then this is the time, so down is good. Thing to note is that Giraffe was one of the most popular of the frameworks. This was 100 times slower than the native. It doesn't mean it was bad, because if 100 times slower meant it took 1 second instead of 10 milliseconds, who cares? But if it meant that it took 100 days instead of 1 day, then maybe you do care. What I found interesting was eventually, about halfway through the paper, you discovered that native meant they did it in MPI, which is the message passing interface that I have been working on for a long time. Okay, so I did want to have a little diversion on the HPC side, because again, I think the focus and concern is often in the wrong place. And so we often talk about the scale, how do I run a program on a system with 1 million or 1 billion cores? And we have systems with over 10 million cores today. And how would I program that? That, frankly, in many ways, that's the easy question. The real questions are getting a better understanding for how the performance runs on a single node. Even understanding how a code would perform on your laptop is in many ways more important. And there's been a focus sometimes on something called performance portability, which is a dream, but it's a dream that I think actually gets in the way of finding good and pragmatic solutions. A lot of the challenge in using HPC systems is really making use of these increasingly complex processors. Whether it's in a machine with 20,000 nodes or the machine that's sitting on your desk. And then I/O is at least as bad for this. In the past, there's been a tight connection between an execution model. The execution model is the way you think the machine works. And I can come back to my point that we tell our students the wrong thing when we're explaining complexity of numerical algorithms, because that's based on an execution model that all of the cost is in doing the floating point computation. That hasn't been true since a little after I was a graduate student, which was shortly after the invention of fire. So an execution model that reflects where the true costs are is important in understanding what is a good algorithm for the problem. Understanding how to create a good algorithm, understanding how to go after tuning a system. This divergence has left us with programming models and systems based on this overly simplistic execution model, which also don't serve us well. And so there is this big mismatch between the user's expectation and system abilities. Often we've said we try to fix this by making the compiler do it. A lot of computer scientists will say nobody should be tuning up their code because the compiler should do it. I'll get back to that in a moment. So I do want to say, in many ways, the easy part is the distributed memory parallelism. There are two hard parts there. One is the algorithms. So you have to be able to have an algorithm that has enough concurrency and that has enough work that doesn't require constant interaction with all of the data everywhere. Once you have that algorithm, expressing it is in fact pretty easy. And so that's why it's either not too hard or it's impossible. One of the big challenges is handling the representation of that distributed data. One criticism that's often leveled against MPI is that it doesn't help you do this. I agree with that criticism. However, it's also a strength because we find that as people put together applications, their distributed data structures are often very specific to their application, which means what you actually need is something that helps you put together something that works with your distributed data structure. MPI doesn't help you, but it doesn't get in the way. And so many people have been able to build tools based on that. Question came up last night at dinner is how old MPI is. MPI is older than some of you. It's about 26, 27 years old now. There was a nice point about a decade ago when I said MPI can now vote. MPI now has to buy its own health insurance. And it has grown a lot from implementing a fairly basic model of based on what's called communicating sequential processes to one that embraces a number of parallel computing models. So that's why I prefer to call it a parallel computing system that allows you to coordinate applications in different ways. And it is still actively being developed. There was a draft for the next version. It was released at our annual supercomputing meeting in Dallas last year. We'll say that applications are still mostly MPI everywhere. That means on every core, they're running a separate MPI process. For our machine, Blue Waters, we did a workload study, which you can look at. And one of the reasons for that comes back to my point that it's not just a floating point. One of the things that MPI everywhere gives you is a very effective way to manage memory locality. And it turns out memory locality is often very critical for performance. And so the bad news is it makes you manage it. The good news is it doesn't get in your way. In fact, in some sense, the good news is it makes you manage it, so it makes you manage it instead of pretend that it's not there. There are a number of challenges. I'd be happy to talk about those during the rest of the day. The hard part really is internode performance. And this is just one example. A lot of performance comes from parallelism now, so a lot of it is multiple cores, but a lot of that is instruction level parallelism, so vectorization within a core. A lot of applications actually don't vectorize very well, and a couple of years ago we looked at a bunch of code that we had a smart graduate student was able to vectorize all of that code. Okay, so the compilers are supposed to be as good as people. How good are they? Well, none of them could vectorize all the code the graduate student. So there's 21 examples that none of them could do at all. And no compiler dominated all the other compilers. There was some loop for which each compiler was able to vectorize that no other compiler was able to. I/O is often also overlooked and pretty much by everybody. Part of it is everybody thinks I/O is awful, and so the expectation drives the fact that it's awful. Two examples from our group. We had one example where it was it's a fluid dynamics calculation. They read in a description file and do some computations. Thing runs for a day. Turned out it was taking an hour and a half to read the description file. Well, that was only like 10% of the run, so that's okay. Then we were trying to do some debugging where when we read the description file, take one step and exit. All right. And I was, figured that would take a few seconds. I was taking an hour and a half. It turned out no one had just done a performance model. How fast should we be able to read that data? It wasn't that big. We actually reduced the amount of code by taking advantage of some features in MPI, and the time went from 4,500 seconds to 1 second. At 1 second, I'm still not happy because if I look at the performance, that's too slow. but it's now within a factor of maybe 4. We were then able to take that code to another application in quantum chromodynamics, so that's the standard model of physics, and that one was merely 48 times faster. Again, because those things run forever, so nobody was paying attention to it. But that was a lot of computed value. And if we look at how bad it is, we did a study where we looked at some of these systems, and I am almost done. So the big thing here is, so this is the number of applications that achieved a certain performance. So very few applications achieved 0.1% of the available performance. And that's a factor of 1,000 over there. So, okay, so some of the challenges. Popular focus on the computation, that's not necessarily where the issues are. A lot of it's due to memory. So is the data there? How easy is it to access? On these systems, sort of the execution model, data moves in lumps. There are different size lumps depending on where the thing is in memory. Algorithms have to think about those lumps. It does make it a little harder, but that's true. There are, however, a hierarchy of tools, so I don't want to scare you about this, but make sure that you adopt tools at the right levels. So I'm going to close by just quickly mentioning there's a lot of resources that are available. National Science Foundation provides resources both through Exceed and a thing called the PRAC, which is for the high-end system. The Department of Energy has a program called Insight, which is quite open and provides access to their big supercomputers. A lot of the other agencies have their own things. For example, the DoD modernization program has stuff. A lot of institutions provide resources. We do, some of our partners do. NSF is increasingly looking to the institutions to provide resources at that scale. There are cloud resources. Cycles can't be stored, so if you're really, really flexible, everybody calls it something different, but there's a way to essentially get stuff at a steep discount because they haven't been able to sell it. There are good ways to request the time. These slides will be available, so you don't need to go through this very much. Should take advantage of exploratory or startup allocations. Focus on the science. Make sure you can show that you're using the system wisely. So that's another reason to use these sort of startup applications, to show that we're using this wisely, because all these systems are oversubscribed. The Exceed ones are oversubscribed by 5-fold. The DOE ones, I think, are even worse. So I did want to close by saying just a teeny bit about clouds. So cloud computing means a lot of things, but a lot of it is like load sharing among users, flexible allocation of demand, there's often a lot of good data frameworks and software sharing. Nothing's free. An interesting thing about clouds is that if you use a machine about 30% of the time or less, the cloud is going to save you money. If you can keep your machine busy all of the time, the cloud is going to cost you money. And this has been shown over and over again in many disciplines. We have a member of our advisory board who retired from a financial firm, and a third was essentially their metric, is that if they were going to keep the machine more than a third busy, they would buy a system. If it was less than a third, they'd do it on the cloud. There are a number of studies. There was a very, very detailed one that DOE did a while back. We did an update in our National Academy report. NASA did another one recently. The rule here is for so many other things is you don't have to believe anybody, but you do have to do the numbers, and you have to do them carefully. I don't want you to go away thinking that I'm opposed to clouds. They actually have a very important role. They give you access to different systems. There's a lot of innovation going on in that space, so taking advantage of that, and it really can complement center resources. And I did want to show this example for a personal reason. About 2 years ago, Amazon, a team at Clemson working with Amazon ran on 1.4 million cores concurrently. That's more than I've ever run on. The personal reason is that's my son, who also discovered a bug in the Amazon software. So the paper was delayed while the lawyers argued about it. And it was really fun to be at one of these presentations in Washington where somebody put up a slide that looks kind of familiar there. So in summary, high-performance computing really is any place where performance is important. The technology is mostly familiar. There are, of course, some things that are a little different, but it is mostly familiar. Don't be scared of it. To take advantage of it, you need parallelism somewhere. Parallelism might be separate things to do. Parallelism may be very tightly coupled or something in the middle. The technology is going through a disruptive period, so we're going to see lots of changes, and that means there are lots of opportunities for doing new algorithms and working with people who are trying new things. It also means that it's going to be disruptive, and that there are many sources for HPC help. Starting with me today, I'm happy to talk with anybody. And then I did have a few questions that I'm curious about in terms of working with this community and seeing what HPC can do to help accelerate your science. Thank you.